Alright, welcome. Today we'll be talking about infinite sequence and series. Okay, now first off, an infinite geometric series is going to be this. So the only time this can happen though is if the absolute value of the common ratio is actually less than 1. Okay, so if you take a look at this, this actually looks very familiar. This actually looks like the series of an actual series, well, the sum of the series of a finite geometric series. Okay, and it's going to be 1 minus r to the nth power. Okay, and let me explain where this went. Okay, all right, so looking at an infinite geometric series, what we're going to say is if a geometric series, if it goes to infinity, that means that n approaches infinity. So we would say n goes to infinity. Okay, well, if you think about it, if the number is less than 1 and we raise it to infinity, this number is getting closer and closer to 0. So this number actually becomes 0 at some point. Our calculators will work with it and just say, oh, you know, that's 0. That's just, I'm going to round down. Okay, well, if that just becomes 0, then 1 minus 0 is 1, and that's just going to be a sub 1 divided by 1 minus r. Forgot to put the sub 1 in there. There we go. Alright, so we actually are missing this, but in actuality, we are taking account for it because of this new situation of where n goes to infinity. Okay, and that brings up something that we want to talk about, which is limits. But first off, when you're dealing with an infinite geometric series, if and only if the absolute value of r is less than 1, then you could take the first term and divide it by 1 minus the ratio, and you would actually find the sum pretty easily. Okay. Now, if the limit is true for this situation actually leads into limits, and this leads into calculus. Okay, then we can talk about other situations where n does approach infinity, and there's some really cool tricks to actually work with it. Okay, now if n goes to infinity here, we're going to notice that it's going to be 1 plus 3 times infinity squared divided by infinity squared. So this is just going to go to infinity. Okay, but if you check it graphically and you look at this as n goes to the right, and when we talk about n and you're looking at a graph, take a gander of what x is. Okay, you would probably see that it approaches a different number. Okay, so there's some tricks to actually work with here that actually make some sense. So first off, the most viable working solution to work with this is substitution. But when you're plugging in infinity, that's not going to be an option. Okay, so when we're doing limits later in calculus, we're working on it at the end of this semester. Okay, substitution is a very good method to work with. Step number 2 is just do some straight up simplifying. Okay, so simplifying actually helps work with the situation a little bit. If you notice I have an n squared on the bottom, I'm going to divide both terms by n squared. Okay, and so what do I have? I have 1 over n squared plus 3, and it just works like that. Well, if you think about it, if I plug in a really large number in for n squared, I'm going to get a really small fraction, and this number is actually going to approach 0. So this limit actually approaches 3. Okay, and we're all about approaching. We're all not about getting exactly there, but we are about approaching. Okay. All right, so that's one trick of working with limits that will actually be very helpful. Okay, another trick is, okay, notice the biggest exponent variable and divide everything by that. So on the top, I'm going to divide everything by n squared, so I'm going to have 5 plus 1 divided by n minus 4 divided by n squared. Okay. And on the bottom, it's going to be 1 plus 1 divided by n squared. Okay, now if you notice, when I plug in a infinity number or a number really close to infinity in these 3 situations, okay, I'm going to get zeros in all of those. So this will actually turn into 5 plus 0 plus 0, or minus 0. Okay, and then on the bottom of this actual fraction, I'm going to get 1 plus 0. Okay, oops, let's do this again, 1 plus 0. Okay, and as you can see, that also just simplifies just down to 5. Okay, now if I check this graphically, in other words, I graph it and then go far to the right and see where the answer actually approaches, I'd actually see it approach 5. Let's see that now. Alright, so what I have here is both graphs in representation of x instead of n. Okay, and the first one we're going to take a look at is 1 plus 3x squared over x squared. And if you notice, I'm going to approach a certain number. As I drag out here, I'm going to actually approach 3 on the right. Okay, right. And as you can see, no matter how close I get, I'm not actually going to get 3 until the calculator really gets lazy and starts just plugging in 3. But this one is actually a very cool way to do another way of looking at representations. Now, if you'd like to see what the limit is as it goes to negative infinity, you would just go over here and you would see it also approaches 3 as well. So that's kind of a cool thing about graphically looking at it. Okay, now here's the graph of the second one. Now if I just graph the top part, I would actually get a really nice, really skinny parabola. Okay, but as you can see, as we graph this one, my y value actually approaches 5 from the bottom. It's actually about 5.99 something. Okay. Alright. So, just as I work with it, guys, just please understand when you're working with this stuff, it's really cool to see where your number actually approaches, okay? Alright? Okay. Now, I know I started talking about some tricks to working with limits as you go and stuff. Divide everything by biggest variable exponent. Okay. Alright, I did talk about this way. There are some rules for limits. You can actually take the limit of two functions, just add them together. I did some interesting ideas thinking about what if n approached infinity. But what would you actually do with the rules is you would actually take them and just work them in here and do the limit of each one. Like, for example, the limit of a constant is just a constant. The limit of something over x is actually, as n approaches infinity, is 0. The same with this one and this one right here, and the limit of a constant would actually be there. And what I would do is I would do the limit. What you could actually do is you could actually do the limits of everything across and then everything below, and then you would divide those two results. Now that's only given that you have no zeros on the bottom, because you can't divide by 0. So if this first one had turned into the limit as 0, 0 plus 0 is 0, and obviously 5 over 0 does not work, okay, as we work with that. Alright, now you're going to learn a lot of tricks in this, and if you'd like to go, you can actually go into the message board and go to the calculus and learn how to define limits analytically by looking at that document, okay? Alright, but for right now, just substitution and simplifying are some of the tricks you can actually use to find limits that you'll be working with. And just think about it, what's happening to n as n approaches infinity as you work with this, okay? Alright, now some actual cool stuff that will actually help out. Rewriting, repeating decimals as fractions. This is actually cool because you can actually use an infinite sum or series, okay? And so here I've actually rewritten it as a sum of an infinite set of fractions as we work this way. Okay, well, first off, I know the first term is actually going to be this one right here. It's going to be 867 over 1,000. Okay, and I know that the common ratio is actually going to be 1 over 1,000. And what I'm going to do is find that common ratio is I just divide the second one by the first one and I get it. Okay, so what I do is I actually find the sum. So the sum is actually going to be the first part, so 867, okay, over 1,000. Okay, so that's the first part, okay, and then we're going to divide by 1 minus 1 over 1,000, which actually turns into 999 over 1,000. Okay. All right. Now, when I subtract those two, that's pretty easy. So what I'm going to do is I'm going to switch it and multiply. I'm going to flip it and multiply because I'm going to multiply by the reciprocal. And I should get 867 divided by 999. Okay. Now just checking it real fast with my calculator. You can actually reduce this because 3 can go into both. 289 divided by 333. Okay, all right. And so what we've done is we've rewritten a repeating decimal because we know the sum of an actual infinite geometric series where the ratio is less than 1. We can actually rewrite it because this is going to be the actual sum. So you can use this to actually work with it. Okay. All right, and that's it for working with infinite sums and sequences. I'll talk to you later. Oh, and the beginnings of limits. I'll talk to you later. Bye.